Good morning, everyone. Thank you for coming out and sharing your morning in this talk. Let's just get started because we have a lot to get through. So let's start here. We start at T0, and this is a very special kind of T0 because before this T0, absolutely nothing exists, not even the concept of existence. This T0 is the beginning of the universe, and let's see what we know and what we do not know about it. As it turns out, what happened in the first millionth of a second, we have absolutely no idea. Whoever tells you they know, they are lying. We have no clue what happened in the first millionth of a second of the beginning of the universe. Apparently, at 10 to the minus 6 seconds after this Big Bang, we do know, or we have a much better grasp of what actually was happening. So there was this singularity, there was this point, and then, boom, I don't even know if it made a sound. No one was there to hear it. And very shortly after, at about 1,000 seconds after this explosion happened, we had starting having heavy particles forming one another. And a very special one is this one, lithium, so the number 3 in the periodic chart of elements. And I find something remarkable. If you yourself or you know someone that is unfortunate enough to have a bipolar disorder, you may know that they can be given a medicine based on lithium to improve the firing on the brain. Nobody really knows how it works, but it does work. I find it remarkable that something that was created 10 to the 3 seconds after the Big Bang, and that's when it was created. It was not created yesterday. It has been alive for 13.8 billion years, can affect our way of thinking, can affect our very existence in such remarkable ways. And this element is very special. Of course, there's the lithium batteries, but you know, people, computers. This is the oldest selfie that ever exists. This is the microwave background radiation. It is an actual picture, so it's not an optical picture, it's on a microwave. And what it shows is the difference in temperature in the whole sky that we have from a mission called WMAP. What you are seeing here is a variation of plus minus 200 microkelvins. And where you see the hot spots, the little bit hotter spots, is where matter started to accrete to form what we now know as galaxies, planets, etc. So we keep moving along on this evolution of the universe. And then we enter to 150 to 800 million years after this T0. And we have these elements here, carbon, hydrogen, oxygen, nitrogen, sulfur, and phosphorus. And those are the blocks of life. Life cannot exist without these elements. And they were created just very, very early on the beginning of the universe. And again, we come from these atoms that were created during that process. Tagging along, let me skip a few millions of years, and we come to 2 billion years after that T0. And what we have is the creation of macro structures. So there is certain regions of the universe are more dense in matter than other regions, and the gravity already exists and it starts coming together. And we have these clouds starting to come together and start forming the stuff. And then in about 4 billion years after that T0, we have the galaxies. As you know, and you may have seen this picture before, was taken by the Hubble Space Telescope. They just pointed at a very tiny part of the universe and just let it there with a very long exposure. And every single tiny dot that you see there is a galaxy like ours with billions of stars, with a massive history, impossible to understand exactly what's going on in there. So we are only 4 billion years after that very special kind of T0. Let me skip 2 billion years and get to a special galaxy that was, you know, it was just a bunch of gas and particles moving, and at some point it stabilized along an axis, so its angular momentum was starting to stabilize. And this stabilization enabled the creation of our sun. So about 9 billion years after that T0, some of that gas started coalescing together, it keeps coming together, and when enough of it comes together into a single point, gravity starts causing the fusion, and then there's heat, and we have a star that it was a special star because it is our sun. Then about 0.25 billion years after that, so 9.25 billion years ago, in the remaining of that star, the sun, a little planet was starting to be formed, and that was planet Earth. That's our home, about 9.25 billion years after that T0. And everything was going great. It was hot because it had been accreting, but it was, you know, everything was safe and beautiful until, you know, something hit us, something probably the size of Mars. And then, you know, everything had to start over from scratch, but this gave us something very special because it gave us our moon. And without our moon, our planet would just not be able to sustain life. It gives us the tides, etc. And, we just keep moving along. And about 10.7 billion years into the evolution, our planet had these bacteria that were formed. The very special property of these bacteria, the cyanobacteria that they call them now, is that they were able to produce oxygen. So then our atmosphere was capable of producing oxygen. And life started to be creating. As you can imagine, I'm skipping through a few details. 13.4 billion years later, on Earth, we had sharks. And that's my best rendition of a shark. Sorry, I could not draw anything better, so just imagine the shark. I find it remarkable that sharks are older than trees. Sharks have been around for a long, long, long time, and that is 13.4 billion years after that T0, we got sharks on our planet. Then a little bit later, we got dinosaurs. So that's a T-Rex. That's an actual skeleton. I took the picture. Well, not me. I took the picture from the internet. I didn't take the picture of the T-Rex. And then everything was going great. We had the dinosaurs, and they were, moving along and doing their Jurassic stuff. And then we had a comet hit in Mexico. I'm from Mexico, so please don't take it on me. It wasn't my fault. So in the Yucatan Peninsula, this comet came, or that is the most accepted theory, at least. And what you're seeing there is some gravity variations on that Chicxulub crater that is there, and that wiped off all the dinosaurs. Well, not all of them. Some of them evolved to be birds. Talk about bad luck. And then 13.77 billion years ago, that very special T0 is when modern human anatomy came about. And this, I'm skipping over the Neanderthal, etc., but that is the modern human anatomy. And then 13.8 billion years, we come to today. And we come again to this little dot. And that little dot is what our understanding of everything that happened before, all this story that we went through, that's what it would be if we did not go and explore space. So it is very important that we choose in this junction that we find ourselves. We just, assume that something happened, assume that we're here for some reason that we philosophically will find out, or we go out to space and try to determine exactly what went on. And this is when we enter into the exploration. So this motivates exploration of space, understanding all this history, what happened. We have been alive for a negligible amount of all this history, but I find it remarkable that we have the capacity to understand everything that happened before. If you're interested in the year-by-year history, good luck. There's lots of books. I honestly don't understand it all, but let's try to see how do we go about opening up this dot, which at this point represent our understanding. So the first one, again, skipping over a few other important contributors. The first one that unlocked the universe, in my taste, was Isaac Newton. Of course, a very observant and very capable mind that decided to write his Principia Mathematica, and with that really told us in his three laws what's up with this that we call existence and reality and physics. And one diagram that I believe it was drawn by he himself, it's the initial idea of getting out of Earth and going into space. So what you are seeing there, it's a little mountain, that point V, and essentially the way he reasoned was, if I grab a ball and I throw it or whatever, I grab something and I throw it on top of a mountain, it's gonna fall. If I, throw it harder, it's gonna travel farther, so on and so forth. Then at some point, I'll throw it with such a speed that by the time it falls, it won't have time and it will hit me in the back of the head. Oops, sorry. And that is a satellite. So he came up with the concept of a satellite just by imagining, throwing from the top of that mountain, and you have that D, E, F, G, etc., and then until you come and hits it to the back of the head. So in space, stuff doesn't orbit. I mean, we call it orbiting, but what stuff is doing, stuff is falling, but doesn't fall down, it falls around. And then you have to have a minimum speed, and your speed determines the period with which you orbit the body, etc. So this falling around is the original conception of maybe we can get out of here and into that space. Then the fooling around, because as it turns out, nothing really works like this. And I cannot even start to enter into the special and general relativity. Newton is the one who gave us the laws of gravity and calculus. I know, Leibniz, two teams. But Einstein's theory is really a much better representation. But as it turns out, and I hope you can see today, with Newton's laws, we can do remarkable work. And so there's just that guy. I want to acknowledge him. But we won't touch a lot into his theory. Очень хорошо, for those of you from Russia. Shortly after these ideas, we got the launch of Sputnik, 1957, the first man-made object, human-made object that went onto space. It was an amazing thing. It instilled fear in the United States. It instilled awe, and we quickly had to respond. So then Jet Propulsion Laboratory, where I used to work, decided that, the military decided that somebody had to build a satellite and somebody had to launch it, and they picked JPL. And then shortly after the launch of Sputnik, JPL launched Explorer 1, the first American satellite. And then the race was on, and the race was thankfully for exploration. Sure, the original motivation was the Cold War, and we had all these issues going on. But it was wonderful that in this show of capability between two countries, we got to discover so much. So let's see the force of math. Just, a little bit going back to high school, you get the rate of change of momentum has to be equal to the forces acting on an object, right? And then you can say like, okay, well, the momentum is the mass times the velocity. And then you can say that the mass has to be constant because, something is not excreting matter. And then, so you can take it out of the derivative, and you get this mass times the derivative of the velocity with respect to time has to be equal to the forces. So that's the force of math. And then, on the other hand, you have the Newton's laws of gravity. That tells you that the force of gravity between two objects is the product of their masses divided by the square of the distance between them, times this constant, the gravitational constant. But we also, from the previous slide, know what the force is supposed to be from a calculus perspective, so we can equal those two equations. And we end up with that the derivative of the velocity has to be, the little m is on two sides, so I cancel it. Is this gravitational constant times the mass of the big body divided by the square of the distances. And then if you notice the last v is now in bold because now it's a vector. And the reason why I made it a vector is because I just multiplied it by the line that joins the two centers. And I put a minus because the force is attractive. So it's attracting, and that force is along that line. So now we have a vector. So this is great. Now that means that we have 6 differential equations to describe the motion of the spacecraft. We have the derivative of position, by definition is the velocity, and the derivative of the velocity, which is the acceleration, is this minus mu, which now is g times m, times r over r cubed. So now this is a vector, 6 differential equations for that point mass. I'm not going to be talking about the attitude of the spacecraft, which has the other 6 differential equations and other stuff. So that's the math of force. And this is a fool. I entered JPL in 2009, and I said, okay, I'm going to go, I'm going to do it, I'm going to understand everything there is to understand about a spacecraft. I'm going to know everything there is to know about space travel. That's my first day. I'm proudly holding Cassini's navigation program, and I was going to do the maneuvers so that Cassini would, execute its merry way around Saturn. I was such a fool. Those differential equations that I showed you, the 6 ones, you can try it yourself, and I'll post some code on GitHub so that you can do it. What I did here is I just tried to say, okay, give me the position of the Earth and the Moon, well, the Moon relative to the Earth, at the beginning of CppCon 2016. And then just use the GM of the Earth, that mu stuff, and just simulate those differential equations just forward up until today, so 1 year. Do they predict? So let's see here. I'll use the cursor here. We can see that in the beginning, the 2 lines are really riding on each other. So that's pretty good. But then, shortly after, what is this, about a month, I'm already off by what, like 4 or 5? What are the units? Earth radii? So I'm off by 2 Earths. That's probably an unacceptable distance. And of course, as I move on, the error just becomes, we should say, astronomical. It's pretty bad. Or is it pretty bad? So we can take the 2 attitudes, right? It can be awful because, by the time we are in 365 days, I'm off by like 60 Earth radii. So essentially, I'm pointing you the other way. So that's bad. But I also find that it's really encouraging that with so little differential equations and so little knowledge, you can predict it for 30 days. So that's pretty cool. And again, no cheating here. Is just grab whatever. Also has an analytical solution. I won't enter into it. You can solve Kepler's equation for the two-body problem. But you can just grab the equations, put them in Python, use SciPy ODInt, and just propagate them, and you get that. Whatever, 20 lines of code or something like that. That gives you 30 days of where the moon is. So the force of reality is that, of course, that's not how stuff moves in space. We not only have the force of the central body, we also have many other forces. And the reality is that you have to be adding these forces onto that vector to be able to really reflect everything that is acting on the object that you are trying to model the motion for. So what kind of accelerations or what kind of forces are acting on the body? We have many. I'm going to try to enumerate a few. We have n-body perturbations. The first one, you have, not only the moon, but you also have the sun, which kind of matters, considering that it accounts for about 99% of the mass of the entire solar system. Doesn't seem reasonable to ignore the sun. We have the moon doesn't really orbit the Earth. They orbit the barycenter of one another. Also, they are not perfect spheres, so we have this gravitational potential that has to be modeled differently. Big bodies have a bulge in the middle, and and they are squished at the top. And then there are other bodies that are not even round, that they just have an irregular shape, like the smaller asteroids. If there are rings, like in Saturn, for example, the rings do exert a gravitational perturbation. They are quite heavy. And of course, the potential of the ring system is not the same as the potential of a sphere. So you have to model that as well. You have the solar radiation pressure, like it is, there's literal solar wind that it is pushing on the faces mechanically and, moving everything forward. And you only need very tiny accelerations over an extended period of time to have this drift that keeps moving on. We have relativistic corrections, so it is true, and they do matter, and we do account for them when we model the spacecraft motion. They are not as important when you are just considering short-term variation, but when you are considering very precise timing, for example, in the GPS constellation around Earth, or stuff that is very close to the sun, for example, Mercury, you just cannot account for their motion without correcting for relativity. We have atmospheric drag for satellites that are low in the Earth orbit, or if you're trying to enter into Mars, you need to take into account the atmosphere. And it doesn't have to be a thick atmosphere. It can be completely a very thin atmosphere. But again, small effects over an extended period of time can make a lot of difference. And of course, you have the spacecraft thrust. You need to know when to fire your engines, in what direction to fire your engines, and with the ISP, everything that's going to happen, how aligned you are. And then you start putting this all together onto that right-hand side that I showed, this sum of forces. So as I will show later, our code is just essentially that. It's just a way to model each one of these different things that they can be modeled in different manners and just adding them onto that vector of forces so that you end up with differential equations that then you use a good propagator and you go ahead and solve it. But that's not all of it. We also have a lot of frames of reference. The only way that Newton's laws work is if they are in an inertial frame. What that means is that frame cannot be accelerated, and we also know that doesn't exist. That's just a construction, of the human mind. So what we do is we say, okay, refer the motion to the barycenter of the solar system. We'll take that as inertial. Then imagine that there's a clock ticking there. So that's, put it there, and however that clock ticks, that's our clock. And then everything you do something away from the solar system barycenter with a clock ticking on the solar system barycenter has to start, taking into account the different frames of reference, the relationship between the clocks themselves, etc. We have different shape models, as I mentioned before. Not everything is a sphere. Not everything can be modeled with spherical harmonics. Sometimes they use plates. Sometimes they use triangles. Sometimes they use cubes. So we have many different ways to model the shape of an object. Temperature models. How is the temperature radiating on the spacecraft? There's many ways to do that. Radiation models, something like Jupiter, has the strongest radiation in the solar system. And you need to do all these models, and then these are represented by a collection of data. It's like a shell that you have to interpolate and find the correct shell, and then find the 8 corners, and then interpolate like this, and then like that, and then like this, and you have lots of data. So quite complicated. Added to dynamics, I said, I'm not going to mention it, but you have a body that is, distributed, and it's not the same being like this than being like that, and where's the center of mass, and so on. Aerothermodynamics, if you're entering into Mars, you're hypersonic relative to the CO2 atmosphere of Mars. So you're heating very fast. You're also dropping heat very fast from the heat shields. And of course, you're getting mechanical motion on the spacecraft. You got to model the instruments. So you have to model the camera, the aberration, the temperature. Where is it looking at? Like whether you're pointing it correctly. And not everything is a camera. Some are radars and so on and so forth. All the telecom, you have your data. Your hard drive is full. You're in Jupiter, and you gotta give it to someone, and it's not gonna be FedEx. So you have to find Earth. You look at Earth, and then you first look at the sun, and then within the sun you look at Earth, and then you point your antenna, and then hopefully the Earth is spinning at well, not hopefully, you of course model that. That's kind of someone's job to make sure that there's an antenna ready to receive this communication. So that's the job of the Deep Space Network from JPL as well. They have 3 antennas. California, Madrid, and Goldstone, and Canberra, Australia, about 120 degrees separated by one another, so that when the Earth rotates, there's always antennas listening to space. You got to model the ground stations themselves, because the ground does move up and down, and that matters. Even if it's 60 centimeters with the antenna, it does matter where the ground moved. And there's an international organization based in France, the International Earth Rotation Service, that gives you the parameters of that model where Earth is and how is the Earth's inertia tensor in that moment. So you have to use it. I think they update it once a week, I guess depending what kind of work you're trying to do. And then the avionics. Everything that I've been talking about is just how the stuff moves, like the physics of the thing, not how you make it do that. That's all the avionics system. I believe there was a talk yesterday, which I'm looking forward to watching YouTube. Unfortunately, could not attend it. But everything that goes into the flight computer, I'm not talking about that. That is massively complex. It's an entire topic in and of itself. And I would say about 40% of the cost of a space mission is developing, verifying, and validating the avionics system. And many other things that I'm not even taking into account right now. So the computers to the rescue. What we have here are the original computers. Those are employees of JPL back in the day, that they were the ones that had to figure out this whole thing. The people would come, give them the models, and they would, by hand, go and compute everything, and just had their summing or their adding machines, and they had to figure out. And I've been told, maybe that's apocryphal, but that the way they would propagate differential equations was literally sitting behind one another, and then just do one step of the Runge-Kutta, and just passing it behind to do the next step, so that people could verify, and then the last one would come to the front and just, continue the propagation like this. Like you can imagine your software doing, well, it was real people. And they were called the computers. And maybe you're aware of the movie that is out right now that kind of talks a little bit about this. So the computers to the rescue, they are working, but who comes to the rescue of the computers? So the computer itself, the digital computer, is the one that came to the rescue of the computers people. And now we have there one of these computers. And how do we talk to that adorable thing? With Fortran. That is how we talk about, how we initially talk about to the computer, to the digital computer, with Fortran. I don't need to go through what Fortran is, this initial, the domain-specific, just for scientific computing. It was great. This is for that computer, the IBM 704, which is actually that computer that I'm showing in that picture. And I just thought this was so funny. I'll give you a minute, 30 seconds to read it. Any programming language that says stuff like that should be looked at with skepticism.
So did the value of pi ever change?
I heard that we're planning to move it to 3, just,
Yes, that's true.
So now, Fortran is remarkable for many reasons. But now I'm going to try to explain why is it so prevalent in rocket science. And it's probably something that you have not considered. So this is an actual Fortran example, is in the notation of modern Fortran. So, your implicit none, I hate that. I hear a real foo, an integer bar, and a logical, like a bool, baz. And then there is this thing called a name list. A name list in Fortran, you just declare, you give it a name. In this case, I called it my data. And then here I just said foo, bar, and baz, these three variables that I declared on top, are part of that name list. So now you can read that name list from a standard input. So there is a specific format that is called the NML format, the name list format, that when it's read, it will populate those variables. And similarly, you can just, I don't show it here, but you can spit a name list in the name list format. And here I'm just spitting it in a, oh, by the way, Fortran doesn't print, it spits. I'm just putting what I read, and then that's the program. So this is the actual format itself. You have an ampersand, the name of the name list, the three variables that I had there, and then this terminator. And you can just do it right now. And here is what it had actually read. And if you had, say, saved the variables in a name list format, you would have gotten out something that looks like this. So why do I say this is such an important thing? So this is how actually stuff goes down in the trenches. People come with an algorithm to simulate something very complex. Inevitably, because of all the things that I told you before, that you have to model the clocks and the frames and the constants and the parameters and the ephemeris, then you have this massively parametric problem. And everything has to be consistent. If you use the masses from one calculation, they all have to be from that calculation. So they have to be self-consistent. You cannot use the masses computed from here with the radii computed from there. So it has to be everything consistent. So what people would do is just grab this massive name list, put everything in them, and just distribute it to one another, grab their program, at the top and start saying, you know, MA1A, MA1B, MA1C, and all the parameters, hundreds of them, and then just produce some documentation, which is better than nothing, and distribute it to other people. So then you would grab that name list, do something, save it, and you had another name list, and you have this collection of text files that represent your entire design. Now, because they are text files and they can have comments on them, they can be version controlled, then people became used to working like this. As soon as you write a Fortran program, you have automatically a parser for a language that people understand. People who went to university know how to write this. People know how to read it. You can copy and give it the meaningful names that, you know, my rocket design v1.2 underscore good. You can give it that name and people just keep them. And then people write software. They're like, oh, it's very easy. It's just a name list. I contend that the reason that people use Fortran is because the engineers can do this. They don't have to worry about GUIs. They don't have to worry about input. And it's also a very simple language. It's very straightforward. You just add, multiply, divide, matrix multiply, and you have something to report, spit out your name list. So I found that remarkable. Now, you'll notice that was in a single precision. You can just change something in the compiler. It'll do a double precision. So it has some sort of compiler parameterization as well, which also turns out to be important. And then there's a field of dreams, right? So then there was also the BLAS, the basic linear algebra subroutines, that were also massively important because they provided a common language to describe algebraic operation. There was BLAS level 1, level 2, level 3, then we had LAPAC, and then we had the netlib, this repository of numerical software. So then more people relied on the software available on netlib that was in Fortran, and then people knew the name list, and the names were already there. Then Clive Moller invented MATLAB, which was nothing but a way to speak to Fortran. That was it. It was originally just a wrapper around the netlib, and just literally LAPAC and BLAS. And then we had this book, Numerical Recipes, that had a lot of stuff in Fortran. So people needed to do, Chebyshev interpolation. They would just hit that book, find out how it's done, and it was done in Fortran. Then later, the authors did produce C and C++ versions. So, if you build it, they will come. They created an ecosystem. And the problem is, if they come, they won't leave. and that is exactly what happened. So nobody defends the current practice with Fortran. I don't think anybody would defend it, but people are comfortable. But it's not that Fortran is bad. It is not. It is not meant for user interaction. You cannot interact with the command line, for example. It has many bad things. It's excellent for strictly numerical computing. The problem is people don't use it for that. People use it for everything else in addition to numerical computing. So it's been very difficult, at least for me, to try to convince people to continue doing their Fortran calculations in Fortran because indeed it is a very good language and people know it. But just put the wrapper in a more robust language like C++ that probably you've heard of. So dreaming a solution. This is, approximately how a problem solution for somebody that works in a space or I guess anywhere looks like. You have some time allocated to the setup of the problem, Another time, once you set up the problem in the whatever system you're using to solve it, you actually solve, so that's the computing time, and then you have to post-process your solution, analysis, etc. Now, I believe that currently what's happening is computing is really not that big of a deal for the most part. In 90% of the cases that I have seen in rocket science-like calculations, computing is not the issue. There are special problems for which computing is massive. Of course, absolutely. But for the most part, in the day-to-day life of an engineer, he or she needs to set up the problem in a massive amount of time. When it's finally set up and verified that it is the actual correct problem, then they solve it, which is relatively small in comparison, and then you have this massive set of results that you have to post-process then. So people have been focusing too much on that middle box that is, I believe, small in the 90% of cases, and I believe forgetting the other two things that are outside. Just let me set up my problems correctly, let me ensure that my setup is correct, just go ahead and solve it, and then give me the tools and flexibility to analyze my results and make educated conversations about this. So what did JPL did? I must say, none of the C++ code that I'm presenting here was done by me. This is all done by JPL. Many people, two wonderful in particular, Ted Drain and Scott Evans, they came up about 11 years ago, maybe even more, I don't even know, but at the turn of the century. They came up with this new system called Monty Python. Really, that's the name of the mission operations and navigation trajectory, something, whatever. They just wanted to call it Monty Python. And so it's built around a concept called a BOA, a binary object archive. And what a BOA is essentially like a game component, entity component architecture that everything only has its name and a set of properties. And you have a trajectory that can have a central body, orbiting bodies and polynomial, and everything's like a string. And then in the BOA, you store those strings so you can exchange BOAs with one another. And they kind of, I believe, hit bullseye. And everything is written in C++. And this is I'm illustrating approximately how it's used. So you can just load a BOA from a file. It's a binary format. You can store a new design element in that BOA. It will immediately be available to you and also will be written into the BOA. So you can use it in another process. You can find, it kind of handles all the complexity for you. In this case, we have this ET, it's called ephemeris time, it's some sort of dynamical clock. It can parse a string, and now it allows you that it forces you to specify a clock. And you'll see this thing right here. It manages units. Massively important. It's not boost units, it's another units library like within the Monty system. And it is massively important. It simplifies things dramatically. And as you know, we did lose a spacecraft because we were not careful about that. And then it can, if you say, okay, I want to find the occultation of the sun, the sun has to be here, the moon has to be in front, as seen from the DSS-14 station, with that context in that BOA, and then this is the time span, and then it just, give you the events. So you become very productive. But this is C++, which I love, of course, that's why I'm here. But not everyone does. So BOAs are not the only constrictors, so everything has Python bindings. And everyone works from within Python. As it turns out, this is not an issue. Again, setting up the problem is what takes the time. The little runtime penalty that it has for setting up the problem in Python is very minor. Once it has checked the units and build the things, etc., everything runs at blazing speeds in C++ and is fine. So this is approximately the same. You'll notice that it's very similar to one another. And now, so we have, I cannot, of course, talk about all the computing problems that we have. It's a big universe, so we have very big problems. Here I just have like approximately how it would look in the implementation, programming this right-hand side of the differential equations that we need to solve. Of course, this is just a simplified solution. So this is where I see the power of C++ shining through, and I don't need to convince you of this. So here we just have some status, is the right-hand side. We pass you the vector of the states, y, and I want the y dot, the derivative of those, given those states. Assume that I can read the parameters somewhere. Here I just use this mu equal to 1, appropriate units, and so on. Differential equations, and just, return me whether the radius was greater than 0, which it should be, right? Of course, in reality, it's much more complicated. And there is one thing that we need most often, and is the bane of my existence, and I hate to love it, and that is derivatives. We need derivatives, and they are so important. They are important for solution of nonlinear equations and for optimization. For solution of nonlinear equations, you need the first derivative. For optimization, you need the second derivative, and it's never of a single variable. So you need a Hessian, and it's sparse, and it's massively large, and it's very difficult to compute. So how can you do it? You can do it with finite differences, right? You can just get the forward differences, and you are order h. And as you know, this f of x0 plus h minus f of x0, h is very small. So you have this, catastrophic cancellation. But then if you make h bigger to avoid the catastrophic cancellation, then it's order h. So then you go and reach for the, central differences approach. That's order h squared. Much better, but it still has issues, and you get the signs wrong, and it's just a big pain. So then you can do also complex step differentiation. So this is true. I think it's very cool that that is true. If you evaluate the function at x0 plus I times h, divide by h, and take the imaginary part of that result, that's order h squared, but there's no subtraction. So it's not subject to catastrophic cancellation, and you can get numerical, essentially full precision. It's as if it were analytical. So complex step differentiation is wonderful. Do I have to change anything on here to do any of this? I don't, because it's a template function, right? So this is what makes C++ remarkable. Fortran has an equivalent of templates. It just doesn't work like that. You still have to write it. It has interfaces. You still have to write it. But in the other case, I can just instantiate my function with a complex number, get the result, extract the, at x0 plus 10 to the minus 8 times h, times I, then get the result, get the imaginary part, divide by h, and that's it. I got it analytical. Go try it. It's wonderful. But that's really not the real deal. So I have here my class, real deal. The real deal is to do automatic differentiation. So have the computer, in this case the type system, do it for you. And this is, of course, I did not invent automatic differentiation. This is just conceptual. So let's go back to high school. You have the real deal is my type, and has a value, and it has a derivative. So you remember how to take the derivative of a product. So u times v is so v times the derivative of u plus u times the derivative of v, right? So that's it. That's high school. And then how do you take the derivative of sine? It's cosine. The derivative of cosine is minus sine. And every single derivative has a very simple expression. So in this case, I just wrote this class. Here is just overloading the operator times. So the left-hand side, right-hand side, everything has the value in the derivative. This is the value, so just multiply them. This is the derivative, again, v times u plus u times dv. Then for the sine is sine, that's the value, and the derivative is cosines times the derivative, because you need to chain rule everything, and that's it. Does it work? Let's see. This is a function, sine, cosine, return me this product, and this works. You can copy and compile it. And yeah, error 0. This is wonderful. This is what we need, and this is where C++ can come to the rescue. But it's still not good enough. So if there's any compiler developer here, I believe this can be done in Clang. And I believe this can be done at the compiler level, and somebody will come up with it. It won't be me. But they will just be able to receive an expression, an arithmetic expression, and at the compiler level, emit the derivatives. Because you have already the evaluation tree. You can just, evaluate backward and get it. This is the kind of hope that C++ gives you. If it can do this, and it can, and there are libraries that do automatic differentiation to any order and with the sparse systems, then, we are in a great spot to continue exploring the solar system. So, okay, I've been rambling around. What do you say? What do you say you do here? So what do I actually do? My expertise are gravity-assisted mission design, so something like Cassini or Clipper, planetary protection, ensuring that we do not bring Earth-borne pathogens to other solar system bodies, and that some solar system bodies that we get sample return from don't come and kill us all. Ephemeridess interpolation, meaning where the solar system bodies are. Situational awareness. We have a huge problem with so many pieces of debris orbiting around in space, and we need to be aware of what the situation, I guess that's where the name comes from, and avoiding this Kestrel effect, which would cause this chain reaction and destroy our space assets. CubeSat operations, that's specifically what my startup is trying to do, is just provide spacecraft operations as a service. And my specialty as in core is trajectory optimization. And C++, that's the thing. So that's the trajectory of Cassini. Remarkable mission that, if you were aware, in September 15th, it died like a champ. And this is what it did, approximately. So Cassini was launched in 1997. Its objective was to study the Saturnian system, and it did so by flying by Titan. So it orbits Saturn, but it uses Titan as its engine. Just for you to get an idea of how important is Titan as a gravity assist engine, the entire engine of Cassini itself had about 350 meters per second of available delta V. Fuel in a spacecraft is measured in their capacity of changing speed. So you measure it in delta V. You say it has so much meter per second. So Cassini had 350 total. And every fly by Titan gave us 800. So it is a massive amount of delta V. Mostly what you do when you fly a spacecraft in a gravity-assisted mission, you don't use your fuel for anything but setting up the flybys so that you get this gravity assist, right? So each one of the little dots, the white dots that you see here, are flybys by Titan. The ones that you see here are flybys of Enceladus. We found out that Enceladus has plumes emanating from the South Pole, so therefore it probably has water. And I believe they are positive is actually liquid water, and you know, water equals life, or so far as we know. Other icy satellites, it has many satellites, and then at the end we just entered into the inner parts of the ring. We were orbiting from the out, then we came back from the inside, and then, you know, it just did its thing. I'll show a movie if we have some time at the end, which I believe we are almost there. Thank you. So then Cassini is over. Does that mean that exploration of the outer planets is over? Of course not. The last thing I did before I left was being a member of the mission design team for Europa Clipper. So the next thing that we do is going to Jupiter with a very capable spacecraft, orbiting the planet and looking at Europa. It's the other moon that we believe that if there's life anywhere, there is in Europa. Europa is smaller than planet Earth, obviously. You can compare it to our moon. But if it does have water, and we believe we do, we believe it does, it has more water than planet Earth. And that is, you know, volume going as a cube of the radius. And Earth is very shallow. The deepest ocean on Earth is about 11 kilometers deep. In Europa, it would be like hundreds of kilometers deep. So there's more water there than here. And it is heating because it's coming in and out of Jupiter. And then it has the chemistry. So let's see what we can find there. And here is the interplanetary trajectory, one of them. There's many ways to get there. This was just the one that I used for my design. So this is called an E-Vega trajectory, Earth, Venus, Earth, Earth, gravity assist. So you go to Earth, Venus, and then you fly by Earth, and then you fly by Earth, and then you go there. So that's why it's so loopy. And then you come here to Jupiter. This is G0, is that you use Ganymede to break with a gravity assist. So this is centered in the sun. So that's the sun right there. And then this is centered already at Jupiter. And we start, these guys right here are the flybys of Europa. So you have first exploring 1/4 of the hemisphere, then another 1/4 of the hemisphere, then another 1/4 of the hemisphere, and then another 1/4. These black lines are eclipses that we need to be careful for because it will be a solar-powered mission. And that's how a trajectory looks like. The color coding is just different phases of the mission. So again, with the damn dot. So now, what do we do here? So that initial picture that I showed you of the modern human anatomy is actually a plaque that was put in the Pioneer spacecraft. That's how it looks in the actual spacecraft itself. What it shows is, you know, the human inhabiting Earth. It shows some atoms. It shows our distance to different quasars or pulsars. I don't remember. Encoded the distance in a binary, some sort of binary code. It shows the Earth, you know, Mercury, the Sun, Mercury, Venus, Earth, and then that the little thingy came out of the Earth is in a very childish manner. The other planets, and then this part over here. It looks like the antenna of a Pioneer itself. And the reason why we did that is because we wanted somebody to find it. So we just threw it like a bottle is thrown into the ocean, hoping that somebody someday will know that we existed. So ultimately, that's kind of what we are doing here, just trying to transcend. And the way we aim to do that is by exploring, and we try to understand to make our own reality understandable to us. And if we fail in doing that, at least to tell someone that we, sometime in this massive extent of distance and time, there was a species that existed and that cared to look a little bit farther. So I believe I have a little bit of time. Let me try to show you this thing of my good friend Cassini. And of course, I don't know how to increase the volume, but well, if it doesn't work, just believe me that it's nice. I'll put it on YouTube. Well, it's on YouTube. I'll put the address on the. It's just showing the crash of Cassini, but if it doesn't have audio, we'll just do without it. So, if gravity is keeping you down, give me a ring, and I can help you with your spacecraft. And with that, I'll finish this talk and take any questions that you may have. Thank you.
How are the coordinates of the different bodies in the solar system tracked?
How are the coordinates?
How are they stored? Like, what is the system that you store the
Okay,
location of everything in?
Great question. So, how do we store our rotations and so our orientations, etc.? So, there is a frame rotation system. They can be stored as quaternions, or they can be stored as rotation matrices. And I prefer that when they are stored as quaternions, because then you can get the derivative very easily. We often need the derivative of the rotation as well. And it's just an abstract interface that is from base and then to base, and then you have the name of the base and the name of the target frame. And this forms a tree, right? And this is one of those wonderful computer science problems that, of course, game designers probably have discovered this on their own. But you have this tree that has the base frame, and then the next frame, and then the next frame, and so on. And if you just do this breadth-first traversal from one to the other, if you look at it as a graph, it gives you the minimum number of hops between the 2 points. So it minimizes the number of transformations that you have to do. So the system functions a little bit like that. You are on an arbitrary frame. You need to get to another arbitrary frame. You breadth-first search it. You get the search graph. And it gives you the transformation chain. And the reason why it needs to be so deep, again, like in games, is because you have the camera, which is mounted on the arm, which is mounted on the spacecraft, which is relative to the sun, which is relative to... So it's a very, very extended chain.
Which is the ultimate frame of reference? The root frame of reference.
Yeah, what is the root frame of reference? There are two. So the official one is called ICRF, the International Celestial Reference Frame. And then you can refer it to the ecliptic plane, meaning the average plane where the planets orbit, or you can refer it to the Earth mean equator of the year 2000 at 12 on UTC. And so again, it's doesn't matter what it is as long as it is something, and the one that is most commonly accepted is ICRF frame. Then there's another one called EME 2000, and again, some of them differ by clocks, etc. But in the end, all your calculations will go back to ICRF. And it's a published standard. If you Google ICRF, you'll see how it goes. Of course, the work of many wonderful astronomers to come up with it.
When you're solving the differential equations, how do you determine the time steps for to minimize error or whatever?
So it is. That's an excellent question. It is adaptive step size. So you cannot just. There's a lot of experience that goes into it, but it has to be adaptive step size. So you just have this minimization of the truncation error. You also have to give longer time steps to increase the propagation speed, the speed at which you get the result, and also make it small, but not too small, because then you have truncation error. We use Adams methods as opposed to Runge-Kutta that are a little bit more capable in their throughput and error control. But yeah, error control in propagation of differential equations is an entire topic in and of itself. And there is also the symplecticity, meaning that sometimes you need the energy to be conserved, which is not with Adams or Runge-Kutta methods. Right. So there's the symplectic propagators.
So you do correction for energy then?
If you use symplectic, you just get, for example, Jacobi's constant, and then it has to remain throughout the propagation. But those cannot do adaptive step size. So you have to just pick the step size and stick to it. And if you do Runge-Kutta or Adams or whatever other method, then you have to accept that you will lose energy. And propagation itself, especially gravity-assisted propagation, is a chaotic process. Mm-hmm. So very difficult. It's very hard to predict the future.
Any parts of those that can be done analytically or not at all?
Not really. So the two-body problem has an analytical solution, and it still has to be iterative because Kepler's equation cannot be solved for the eccentric anomaly analytically, so you have to iterate on it. But it has an analytical solution. But the three-body problem and onwards is proven not to have an analytical solution. Yes?
Can you give an estimate what amount of computation is required to compute the trajectory for a mission like Cassini? Like supercomputer for days or like hours, seconds?
the question is how long does it take to compute the trajectory of a mission like Cassini? Not too long. I would say it's in the order of tens of minutes to compute one trajectory given everything else. To do the optimization of a trajectory is something that can take many hours. But for problems like planetary protection, where you need to vary the initial conditions a little bit, essentially you have a covariance matrix and you have to sample it to account for all the disturbances and simulate one time and another time. At the end, you simulate millions or tens of millions of times. That takes many months. And one of the last things I did is try just implementing that planetary protection system in a, just to deploy on the cloud, everything in C++ from scratch. And now it can be done in days. So in about a couple of days, you can get 5 million simulations for planetary protection purposes.
Can you please operate with this point protection problem?
Yeah, you cannot dispose of a spacecraft uncontrolled. You need to throw it to the garbage, if you will. You cannot just say like, okay, it stopped orbiting. So take Cassini, for example. It was out of fuel. It could have remained in the Saturnian system for whatever amount of time. But it could be the case, if we cannot control it, and it's just ballistically, that it could hit, say, Enceladus and contaminate it. Cassini is carrying a nuclear material. It's irresponsible to do that. So then the NASA Office of Planetary Protection, which has conventions with other international organizations, requires everyone to dispose of it controlled. So we decided that it would be, crashing it into Saturn. When you do a mission like Europa Clipper, you could hit Europa if you don't pay attention to what you're doing. So when you have a nominal mission, you extract the covariance, or in other words, the uncertainty of every parameter of that mission, and you sample each one of them and assume that the spacecraft fails, and determining how many instances did the spacecraft actually hit Europa. And then you get probability of failure given impact given failure, of probability of contamination, and so on. You make this Bayesian approach, and that whole analysis is called planetary protection analysis. Yes, of course. Yes.
When concatenating the transformations, so you talked about the transformations.
Mm-hmm.
Do you run in any numerical problems? Like, what kind of number representation do you use?
If we run into any numerical problems in representing the transformations, everything that we do is in double precision. The only thing that has to be done in quadruple precision, which is only implemented in software, is the time for very precise ranging calculations. So our clocks are now super accurate, and they have USOs, the spacecraft ultra-stable oscillators. And sometimes to do the orbit determination, you need quadruple on time only. But everything else, double precision, seems to be good enough.
Continuing on that question, do you need to modify reference frame in order to get better precision? Like if you're doing calculations around Saturn, do you try to make Saturn your reference frame in order to reduce the scales of the double precision?
Absolutely. That is called center switching, and it's also represented as a graph, which also you just do the graph search to do it. So you have this tree, you have the sun, and the barycenter of the planets orbits the sun. And then within the barycenter, you have the central planet, and then you have the satellites of the planet. And then every planet or every body has something called the sphere of influence, so where the gravity dominates. So when you enter the sphere of influence of a body, this tree system does this search again, and then it makes that the center, and then everything else is referred to that, precisely to take advantage of the being closer to the planet that is dominating. Then you get out, and then it center switches again. Very complex process. Well, it's not complex, it's difficult to implement.
Do you get numerical problems when you switch spheres of influence?
Yes, yeah. And at some point you can only compare two trajectories that were propagated with the exact same algorithm. If I come up with my good center switching algorithm and you come up with your own, it's normally accepted that we cannot compare them, precisely because yours is a universe and mine is a different universe. So yes, they introduce errors, and to the point that they become like a singular thing that has to be treated consistently.
Thank you.
Of course. Well, if there are no more questions, I appreciate you attending the talk. Thank you.